Hello, my name is Gabriel Nuzzo, and I'm going to be walking you through my group solution to assignment 1. I worked with the following people shown on screen. So with this assignment, our goal is to launch a rocket with a payload of 200 kilograms into space so that it never returns to Earth. We will be using a two-stage rocket design, where the second stage begins as soon as the first stage runs out of fuel. We want to optimize the amount of fuel in both tanks, where the rocket will have the greatest kinetic energy as it leaves the atmosphere. And then the fuel mass is what we will be computing based on the parameters that we're given and the model that we develop in FlexPDE. We also have a maximum budget of $3 million. My primary role in this assignment was in modeling the rocket trajectory in FlexPDE. This meant having a good understanding of the theory behind the problem so that I could implement it in code. I also assisted in writing some initial Python scripts and writing the team report. Next, I'm going to give an overview of the theory and our analysis code. While in flight, the rocket is subject to three main forces. First, gravity, which is modeled by Newton's universal law of gravitation. We expect that as the rocket flies away from the Earth, this force should decrease since the radius between the rocket's center of mass and the Earth's center of mass increases. It will also decrease because the rocket is losing fuel mass and mass from the engine stages. It also experiences a fluidic drag force from the air in the atmosphere. The air density is modeled using the ideal gas law. As the rocket's altitude increases, we expect the air density around it to decrease until it reaches zero. This will decrease the drag force, all else equal. For our problem, we assume that we can say the rocket has left the atmosphere when the air density reaches zero. Finally, the rocket experiences the thrust force of its own engines, which is equal to the fuel flow rate times the fuel exit speed. We are also given any necessary parameters that we need to solve the problem. We have to figure out an equation for the rocket mass, and we expect that this will decrease linearly due to fuel loss up to some point, and have piecewise gaps due to the dropping of rocket stages. In FlexPDE, we used vector form for simplicity adding forces later on. Here we define our variables, such as fuel mass, flow rates, etc. You can see that we modeled fuel mass 2 as a function of fuel mass 1, assuming that we always want to spend our entire budget for best results. Here's our thrust force, modeled as a piecewise combination of both stages, modeling of gravity, drag, and finally combining of the forces. I also defined expressions for cost and kinetic energy. At the bottom, we output a number of useful values and graphs for analysis, and we export the value of the speed, mass, kinetic energy, total cost, and air density. Running FlexPDE with dummy values, we can evaluate our model's performance. With very small fuel masses, the rocket is only in the air for a minute before crashing to the ground. Adding more fuel, we can see the rocket goes higher as expected and leaves the atmosphere. The mass decreases in a linear and piecewise fashion as we expected, and the air density decreases with altitude. The acceleration due to gravity also decreases as the radius between the rocket and the Earth increases. These results all make sense with our model and what we expect due to physics. If we experiment with some more scaling, such as a humongous mass, we expect that this won't even get off the ground due to the huge weight. And this is the case. Therefore, our results make sense. In Python, we start by importing necessary libraries and initializing our FlexPDE code as a string. We use %s here as a placeholder for fuel mass 1. This will be updated for each value we want to check. Next, we define a function to determine fuel mass 2 from fuel mass 1, assuming we use our entire $3 million budget. This is used in the following function, which determines the theoretical time it takes for the rocket to run out of fuel, which is useful while interpolating our data later. This next part of our code tells the program where to find the outputted flex file. Next, we assign a range of masses using the NumPy arrange method, which returns evenly spaced values with a given interval, and create lists to append our data to. Next, we run our flex code with each mass value and append our FlexPDE data to our lists. Since we want to know the exact time the rocket runs out of fuel as one of our stopping conditions, we use our calculated time from above to find the kinetic energy when there's no fuel left, via linear interpolation. This is appended to our kinetic energies list. To find the maximum kinetic energy in the array of masses and kinetic energies we just found, we use NumPy's argmax method, which returns the indices of a maximum along an axis. Finally, we plot the kinetic energy versus mass 1 and have Python print information about the kinetic energy and masses. To find the maximum kinetic energy as a function of fuel mass 1, we searched for the max value in a series of mass ranges, each progressively getting smaller. While this is not the easiest route, it allowed us to deal with the noise in our data. Other similar search methods would be confused by the many local maxima. Using the methods I described, we found the best combination of fuel masses for stages 1 and 2, and the resulting kinetic energy. These are shown on screen. The value for the fuel masses has an uncertainty of around 0.5 kilograms, since this was the final step size we used to determine its value. The rest of our final values were calculated to an accuracy of 3 decimal places, which is within the range of the given constants. I learned that approaching daunting problems by focusing on each part of the problem individually makes them much more doable, and I am proud of what our team achieved. Thank you very much.